My clinical psychologist daughter avoids online journals at all costs because she doesn't think that they're as good as print journals. But at least in statistics, that's changing quickly. The online journals are much faster. You can do much cooler stuff. They just look at the impact factors and realize that publishing in some archaic online journal might not necessarily be your best choice. There's a bias there, obviously. So let's see. Did we make? I should have interchanged the red and the blue as usual. So U.S. Kentucky is red. So we looked before at principal components, right? And let's see. Principal components should be crappy at, I think I want 6 of these, but not beryllium. That's what I've been playing with. I can't use all of them. How many? I have 38, so there are approximately 30 elements that are measured for 23 data points. Obviously, there are lots of ways to get perfect discrimination. I can just get perfect discrimination really easily because I've got more so this is the P greater than N situation, so I have to be a little careful. If I choose the 5 out of the first 6, it turns out beryllium is really good at classifying, so I take it out in my example. So this is principal components based on these 5 elements. And it's not good at classification, right? They're completely overlapping with each other. I guess, I don't know, whatever we do. Maybe I classify things over here as red and things over, but that's not surprising. Right? When we talked about this example, we weren't surprised to see this plot. Now the plot differentiates really well when you have the international data. So depending on the point you're trying to make, that it may be a useful plot. But so I rule out principal components because I'm trying to classify and it's not working well. So I guess I better go to our latest method that we've added to the list, which would be discriminant analysis. Again, the competition in papers is typically between logistic regression and discriminant analysis. But there's a latest, partial least squares is coming up the rear and gaining popularity every day because it tends to beat both of them regularly. Linear discriminant analysis wins if the data is close enough to normally distributed. But that close enough depends on things that we don't know, especially when we have 23 data points. So discriminant analysis, the 2 categories are there. My 6 variables are here. And remember to take out beryllium and say OK. And so I'm making a linear combination, right? So that linear combination is one-dimensional. So I can plot it. And the red ones are mostly over here, and the blue ones are mostly over here. Why is it on a line? Because it's one-dimensional. I can add another discriminant function if I want, just like I can do with partial least squares and principal components. But I choose not to right now. I like the discriminant analysis output, by the way. The partial least squares output is nowhere near as pretty, so I can get my jump friends to work on this. Because it tells me right here, this is how I did. The actual Kentucky ones, I classified 12 out of 16 right. The actual US ones, I got 5 out of 7 right. So I did pretty well. Maybe for next week I'll have a bigger, it'd be better to have a bigger data set where we could have bigger differentiations between them. But so, and I get the probabilities over here. So the probability that they're from Kentucky based on the assumption of normality is the following. And there's the probabilities, and that one kind of sucks. Got 82% chance of being from Kentucky, but really it's in the US one. So that's dramatically wrong. Am I reading this correctly? Now I'm questioning, why are these guys, if that's the probability of being from Kentucky, I don't believe these columns now. So common sense says, what happened here? These guys are from the US, so maybe the notation switches, and for the US ones, it's probably what's happening. So my confidence in the output from discriminant analysis isn't quite as good now. Or maybe I should just read the manual more.
That says probability of predicted.
Yeah, I know, but what does that mean is not clear.
Probability of correct,
Probability of correct classification?
No, the probability that it's from the predicted.
From the
From the
predicted
predicted
group.
group,
Yeah. So eventually I figure it out, right? You guys figure it out before I do. So so it does make sense that these are, so that's a borderline one, right? The 0.51 stuff. These probabilities are basically made up because I have a sample size of 23. I made this assumption of multivariate. I'm not going to, who knows whether that assumption is correct or not. Are these variables normally distributed? I don't know. Am I going to have any evidence that they are? I don't know. I could actually, maybe I should transform them. They probably need a log transformation. Almost every variable needs a log transformation. So would I do better? Oh, that's actually interesting. I got 4 minutes. Instead of going to the, so I can try the other methods. The other methods do sort of the same, by the way. So which one's the best? Don't know. We need some unknowns to classify to see which are best. How are we doing on the assumption of normality for these variables that I'm using? That one's gone. Okay. Well, BE, whatever BE, needs a log transformation. Is arsenic already normally distributed? Don't know. But so maybe log transformations would be a good idea. Should I transform some of them and not others? Ugh. If I'm going to do a log transformation, I'm going to do it on all of them. In general, your log transformation won't hurt you. It'll only help you in the cases that are highly skewed. I'm curious about whether this one will satisfy. So it's really not all that normal, right? Got too many in that group. Why is it? The scales are interesting, right? This one is between -4 and 3. I wonder wonder if some kind of transformation has been done to that data already. If I take the log of that variable, oh, it was B, no. AS is the one that we could take the log of. So we need the data. We're not going to have time to do this. Oh, now I'm screwed. Wait. Oh, so there's the negative. What's going to happen if I take the log? I don't get to take the log of my negative variable. But I really want to take the log of this one, right? I wonder if these have been log transformed already. I wouldn't be surprised. Okay. Column, add multiple columns. We're going to call this log EE. Formula log BE. Okay. I'm just curious in my 1 minute. Much better. Still skewed, right? But I pulled the tail in a lot. So now I got 0 minutes, but that's okay. We'll go here. Analyze. We want to do discriminant analysis.